All right, welcome back. Now we will get into more on plotting, which is the subject matter of chapter 9 for this week. So you can read through chapter 9 before going through this video, and then watch this video and then go and complete the exercises that are assigned for this week in chapter 9. So what this will give us is a little bit more advanced control over some of our plotting options and what we've gone over already. But you should already have the foundations of how to make a plot, particularly since that was on your last exam. So we're going to go ahead and load a built-in data set that comes with the ggplot package, which is the MPG, which gives, we'll do a quick inspection of this data set, but it basically gives us the fuel efficiency of a variety of vehicles and different, whoops, uh, MPG, based off of the manufacturer, the model, the displacement volume, so basically the size of the engine, the year of the vehicle, the number of cylinders, transmission, drivetrain, whether it's forward or rear or four-wheel, the city miles per gallon, the highway miles per gallon. And to be honest, I'm not sure what the FL is, but we won't be using that, so it doesn't really matter. I use glimpse, but we can also look at head if we want to look at what it looks like in terms of column structure. So head is just another way to quote unquote glimpse at our data. It gives you um, a similar kind of peek at the data as you can see from the top versus the bottom. So what we can do is give ourselves a little plot to start with and look at what is the relationship between the engine size and the highway miles per gallon. And if we wanted to look at something like, what about the class of car, two-seater versus compact, mid-size, we might say I want to specify color as my class of car. Uh, and then I can indicate by color which is which within my data set and identify if there's a particular color in one chunk of the data versus the other. So for example, we can see that our pickups down here, as well as our SUVs, tend to be the least fuel efficient, whereas we have more purples and different colors up here. There are a variety of color scales. So if you are into your color scales, there are different color scales that you can use that are colorblind friendly palettes. So that's an important consideration. So you can do grayscales if you want, which might be for some manuscripts if the journal publication still has a charge for color graphs versus non-color graphs. But at the very least, there are also color palettes that are colorblind friendly, that are simple little add-ons, like our colored brewer is one. And then there are a variety of others that you can check out on that. But the key thing here is, so when we specify color by a particular category, we can get color, but we can also specify shape and get different kinds of points. So one thing that we see here is we get a warning that comes up with this, partially because there are not enough shapes available for all of the different classes to each get their own shape. There are other kinds of shapes that we could use if we wanted to provide a discrete scale. So these are all of the options for specific shapes that are available. Some of them are very similar, like for example, 16 and 20 and 19 and 16. So several of those are not super useful in terms of shape options. But if you wanted to specify a specific shape, so for example, I can override the aesthetic and just say shape is equal to 1 here. And what you see is I get this specific shape. But now say I want shape equal to 2. I can then switch to triangles. I can say shape is equal to 6. And then I get the upside down triangles, which is associated with 0.6. So the reason why this is happening in here is that even though I specify that my point, I want shape to be specified for class, when I then add, because remember this is layered, so this is my base, and then when I add onto here, I'm essentially overriding, in this case, the aesthetic of shape equals class to shape equals 6. So that's why my points all look the same and are no longer specific by class. If I just remove that so that I'm not overriding that, I get back to the figure that I had previously. So if you wanted to, you could specify. So for example, it says consider specifying shapes manually if you need to have them. So for example, the default in the shape specification is 6, but I could, for example, specify a shape scale, picking out the specific numbers that I want to use to be able to use a larger scale for shapes. I can also add in multiple things. Like for example, I can also have color is equal to class. It doesn't just have to be shape. So what you'll see here is that it'll provide a different shape and color based off of my specifications. Again, I need to specify different variable here for my shape because I'm essentially running out of them. If we go back up to what my different options are, like say, for example, I chose cylinder. Whoops. Probably because my different variables need to be treated as a factor. There you go. So the reason why I got that previous error is if I look back up here, my cylinder is being treated as a numeric variable. And then when I'm trying to ask for a certain color by a numeric variable, that doesn't really make sense. Sometimes what it'll give you would be a scale for color, which I can show you. But it was the reason why it gave me an error is that it can't make a shape for a numeric variable that shows different numbers if we're treating it as a number. So I could, for example, if I wanted to not have this as a factor and I dropped shape, first I'll show you the plot that we have. So factored here, it gives me my 4-cylinder vehicles, my 6-cylinder vehicles, and my 8-cylinder vehicles. So obviously you can see big differences in highway fuel efficiency based off of the cylinder size. But I could have also, if I've treated it as a numeric, what it will give me is a color gradation scale going from light to dark based off of the numbers. So I'm getting this because it's treating my cylinders not as like a factor 4, a factor 6, and a factor 8. It's treating it as a graded scale from 4 to 8 and providing different colors based off of that. Super useful if you wanted to make heat maps or if you wanted to show some type of gradation of a numeric variable, you can still use color for that. Actually, that's a really nice tool for a variety of situations. But in this case, what I wanted it was to be treated as a factor, and I got an error before because I can't do the same gradation for a shape like I might do for a color. So now I can do a similar type of plot, and what we might have seen, well, what you did see a second ago, is that I can override the aesthetics without necessarily mapping it to the data. And what I mean by that is that in my original ggplot, I specify my aesthetics and I'm mapping it to data. What I mean by that is I'm saying x is equal to this variable, y is equal to that variable. When I'm not mapping it to data, I can just say color equals blue or color equals red, for example. And if I run this, I just get a blue graph for all of my points because I'm saying that they are blue. They're also somewhat transparent. That's specified by an alpha. So alpha essentially tells me how transparent do I want my dots to be. This can be useful if I have a really large data set and there's a lot of overplotting. So when you have multiple data points on top of each other, it gets very, very dark. And when you have multiple data or no data points in a specific area, it's very transparent and easy to see through. So I can change the transparency if I want. And you can see here that I have very little data over here. I have some overplotting here. And here I have several data points all at the same location, indicating overplotting based off of the transparency for the number of data points there. If I wanted to, for example, have, again, this mapped to data, what I could do is say aesthetics, let's say my alpha is equal to cylinder. It will produce different transparency levels based off of the cylinder number that we want, or I could specify color. In here we get our back to our color. So by specifying aesthetics, that means I'm mapping it to my data, meaning that the variable is going to be pulling some value out from the data set itself. If I'm not mapping it to a variable and I'm just saying I want color equal red and I just want all of my data points to be red, I'm not mapping it, I'm just specifying that I want my points to be red. So there I do it outside of an aesthetics call. I could, for example, have both and say I want alpha equal to cylinder. So here I've specified that I want everything red outside of my mapping, and then in my mapping, I want the transparency to be specified by the cylinder number. So as you can see, we do have some other cylinders appearing up here, or actually alpha is a bad choice because overplotting would also produce the same thing. But nonetheless, we could go back to shape if we wanted to. We'll just ignore that would be fine. It would be easier. Of course. I forgot to factor it again. So now I have my various shapes equal to my cylinder variables, and I've specified them all being red. So hopefully that clarifies what we're talking about when we're referring to mapping of the data and whether we do it within a call or without of a call. But because of the nice layered fashion of this is that it basically, this is our highest level, and everything that we specify in here gets automatically passed on to all of the subsequent calls that we make. If we make a call that is in conflict to something that is in the original, then we will overwrite what was in the original with the new value. And we'll show that more in detail in just a second. But what that means is that if you have something up here, it will automatically be inherited by everything below. But if you don't have something, then you're able to specify it over here. And then if I were to add something else like a line, that would then inherit everything that was specified previous to it. So it makes an important kind of trail or sequence of different things that can be filled in. So now coming down to another plot, we can do a couple of different specifications. So take our ggplot, keep our uh, engine size by our miles per gallon on the highway. Now I'm going to add a point and I'm specifying outside of my mapping that I want shape to be the triangle, my fill to be red, and my color to be red. So fill is going to be like the coloring on the inside. So that's important for bars. So one thing that has confused me initially when I was getting started out is if you're trying to make a bar graph, which I almost never do anymore. But anyway, if you're making a bar graph, if you specify color is equal to something, it will just outline the bar with that color. You have to use fill to specify that you want to fill that entire bar in with a specific color. So fill is whether you want to color it in. Color is just the tracing of the particular points. And then we can add, if we wanted to control our y-axis and what appears on our y-axis. We have a variety of options that we can do. So Chord Cartesian is a really nice tool that will allow us to pull our data to specific ranges. So let's say I can do 0 to 30. It doesn't delete any of the data, but what it does is it only makes my y-axis to a specific range that I'm interested in. So say, for example, I wanted to look at, well, let's just look at the relationship between things that are in the 30 to 40 mile per gallon range as a particular category, and I want you to just show me that. Then it will just specify this is my 30 to 40 mile per gallon range. So you can kind of zoom in, zoom out is what Chord Cartesian will do. We can also specify an X limit. So what I'm doing here is saying my Y limits are from the bottom to the top. I could also do my X limits in the exact same way and zoom in on very specific sections of my graph. So I could say X limit is equal to, let's say, 0 to 3. And what you see is I've essentially selected a very specific chunk of my overall data with this. If I remove all of them, I get back to my original data set. Now, the scale Y discrete, there are different types of scales that we can specify. So there's discrete Y scales, but there's also continuous Y scales. So a continuous Y scale is actually what the appropriate one would be here. And that is because we have a continuous measure as our Y variable. And inside, by specifying our scale Y continuous, this gives us a lot of controls in how we want it to look. So for example, I can say my brakes are equal to, say I want it to be 15, 20, 25, 30, and 35. What you'll see is that now my graph has just the labels at the specific brakes that I want it to be at. I could use things like my seek tools, remember that we talked about before. So I could say seek 1 to 40 by 1. And then it will give me each individual mile per gallon that I want. What you'll see here is that it automatically cuts off at 11 because it's going to be doing a couple of different zoom in, zoom out kinds of factoring for me automatically. But then I can go back into my Chord Cartesian and force it to actually show me the whole graph if I want it to. So this is a terrible option that you should never use, but just to demonstrate what you can actually do. So it gives you full control over what your Y limits are, what your breaks are, how you do your breaks. You can also, if you wanted to specify Y lim here. The only difference is, say I specify it to 15 to 30, is a very subtle difference. Let me see. Whoops. Maybe not. Maybe I have forgotten. Just checking scale Y continuous. So I can specify the minor breaks, the labels. So the labels is actually very useful to, no, I think I know what I was trying to do. Is you can also specify a Y lim of say 15 to 30. So here I've specified a Y limit of 15 to 30. The difference here between specifying a Y limit separately or outside of the chord Cartesian is that the Y limit says anything that is outside of these ranges, delete that data and don't plot it. The chord Cartesian says, go ahead and plot it, but just zoom into a specific region. So if you're using Y limits, you could run into trouble if you are computing some type of average, because it'll change where your average is based off of whether you delete that other data or not. Chord Cartesian would allow all of that data to go into your average, but then zoom or exclude certain data points based off of your kind of zoom level of your figure. Y limit, say for example, you had some high outliers and you wanted those to be removed and just compute the average of, say, any mile per gallon from 0 to 40, and if there was a value of, say, like 77 in your data set and you wanted that to be deleted, then Y limit would be the appropriate tool for that. So with labels, for example, what we can do is say breaks equals, let's just say 15. And I could say labels equals something like this. So now what it does is it puts a break at the point that I specified and then gives it a label. And so instead of calling it 15, it calls it mean for me. So this gives you full control over what you want your y-axis to be, so that it keeps that underlying numeric properties, but then has a specific break at a specific level. So say, for example, I wanted this to be at 30 miles per gallon. It then shows me what that is, or say, I don't know, good. So it gives you all kinds of options into what you want your different scales, Y and X axis, to look like. So now by controlling our scales, it gives us more control over what we want our various lines to look like. So let's say, for example, we add a smoother. So the smoother is going to be a statistical smoother, or essentially kind of like a regression line to our data. We can specify what kind of smoother we want. So if we do method equals LM, this would give us a linear model if we wanted it to be. But the nice thing is the default smoother is a Loess smoother, which allows us to get flexibility in our curve. So if we have something that might be non-linear, then it actually is able to pick that up. So we can go back to adding a point so we can see why is it actually picking this up, and you can see that it's essentially seeing that we have a couple of very large engines that actually tail up with relatively efficient uh, highway miles per gallon. So the low S smoother allows you to see if there are kind of non-linear trends in your data. If we had the method is equal to linear, we essentially force it to be linear, whether it truly is linear or not. So now, if we go down here and we add that we wanted a particular line type to be controlled by, say, for example, the drivetrain, whether it was forward, rear, or something else, this actually gives us different smoothers and graphs based off of our. This gives us our different low S smoothers for each of our different drivetrains. And that's because we specified it in the mapping here that our line type is going to be driven by the drivetrain in our data. If I wanted to override this, so say for example, I did not like that, I could specify that I want group is equal to 1 here. And instead of giving me a separate line for each one, I'm basically saying I want a singular line and that my grouping that is my drivetrain is no longer what I want for my smoother, and I want one overall average smoother. So let's say, for example, why might I want that? Maybe I want to change this to my shape is equal to my drivetrain. I want to add my points and my smoother. I get one overall smoother. I can see different shapes for my different types of drivetrains, but my smoother is actually ignoring my different drivetrains. If I don't like that, then I just remove my grouping, and then I get a different line for each one. So we can see that uh, my circles, my rear drives, or my four-wheel drives tend to be lower than are going to be my forward wheel drives. And then my rear wheel drives tend to occupy a very specific space, which typically tends to be very high engine, slightly less fuel efficient. So four-wheel drive is pretty much always less fuel efficient than forward wheel drive, and then rear wheel drive is a specificity to typically my larger engine, bigger vehicles. Okay, so then this just highlights what we just kind of went over by specifying our group factor. Um, we can specify multiple variables if we wanted to. So for example, maybe we want color to be related to our cylinder, but we want our line type to be related to our drivetrain. So we are now plotting the cylinder size as well as the drivetrain, and we can see that pretty much all of our rear wheel vehicles are 8 cylinders, whereas most of our front wheel drives are going to be 4 cylinders, some 6 cylinders. And then we do have some rear wheel drives that tend to be a bit across the board. Here we can change out what we want our graph or our smoother to be categorized by. So instead we can have it categorized by our cylinder size and look at what our fuel efficiency looks like based off of the size and the overall cylinder size. And then again, we can basically do the exact same thing, but now we are specifying our color and our line type to be of the same singular grouping variable, which will be our drivetrain. So we have our four-wheel drives colored by four-wheel drives, our forward wheel drives colored by forward wheel drives, and our rear wheel drives colored by our rear wheel drives. So that, as you can see, we can really extract a lot of information graphically based off of our various types of settings that we can use and built-in smoothers. So this just highlights what we have been looking at. Sorry about my first plot. Is we can have our drivetrain by color, and if I specify, for example, that I want color to be based off of drivetrain in my point here, my GM smoother is not necessarily picking this up. So if I wanted to add in here, I now get my separate lines based off of my drivetrain. But by default, since it's not in my higher level ggplot, it doesn't pick that up. And I might have been, I think I said it previously that it actually passes all left to right, but I actually think now that it only passes from the ggplot statement downward. But this gives us the opportunity to look at different class of vehicles using color and having one singular GM smoother. But if I wanted a GM smoother by each one, I would then have to specify color equals this. And then I get a bunch of warnings probably because I have so many data points next to each other, but I can then get a different smoother for each of my various car classes that I am interested in. And we can see that our SUVs and our pickup trucks are at the bottom. Our two-seaters actually, oddly enough, aren't too bad. And then kind of everything else gets kind of squished together to some degree. But because of this kind of layered manner, this does offer some kind of really interesting opportunities for making graphs that I think are really quite useful. So for example, we can have different data being plotted at different layers. So say, for example, I have my high-level ggplot, which has all of my data, my X and Y, I add my points, but then I could also add, for example, another point where my data is filtering out for two-seaters only and making those red. And then I can have my another point where I am filtering for two-seaters that have an open circle that is colored red and gives me the option to highlight just my two-seaters with a particular type of I guess, specific shape and color feature to it so that these are my key data points that I might want to highlight. And there's a lot of other useful tools about being able to specify different data at different layers of my plot, which we'll go more into in the next section. But this does allow us to, instead of like before, where if, say, for example, we wanted to specify two-seaters only, as you can see, we could do it by class, but it's a very colorful plot and it makes it difficult to say the two-seaters, where are the two-seaters specifically? This highlights very easily exactly where the two-seaters are if you want to show specifically on the graph. So in this case, it does have a particularly useful tool, but where it's most useful is actually in the next section and in the next video. And we'll pick back up there in just a second.